Hello everyone, welcome to video 5 part 3. In video 5 we are trying to calibrate the Danube watershed in the Danube Basin. This was part of our larger European project, as you remember, the details of which you can find in these two articles. In the first video, I showed you some pre-calibration steps just to make sure that your model is correct before you try to calibrate it. And in this, at the end of this, we produce a pre-calibration simulation. And as you call, the pre-calibration simulation is the initial simulation of your model without any calibration. And here we decide whether it's we can go ahead with calibration or not. Sometimes the simulations are not very good because the model is not correct, and there is no point in calibrating such a model. But with this initial simulation here, you see that there are quite a few negative nice subcliffs, but overall there are small values and there are some positive nice subcliffs. So we decided that the model was good enough to calibrate and we could improve it. In video number 2, we looked at the watershed and we saw there was a lot of urban areas, a lot of agricultural areas and forests, and there was a lot of activity. It's a Danube watershed. It's a very complicated watershed. There were dams, there were water storages, there were water reservoirs, and so on and so forth. So at the end of that, I said we have to keep the reality in mind, and there isn't all the information that we have. I mean, we had some information from the general European project. We accounted for agricultural activities, we accounted for some point sources from water treatment plants and so on and so forth, but still there are a lot of things happening there that we did not account in the model. In that video number 2, the first thing we did was to fit T-labs and P-labs, as we should always do, and then we fixed those parameters. After we fitted T-labs and P-labs, there were fewer number of negative nice subcliffs. This was our initial. There were quite a few negative ones, but here we only have 2 negative nice subcliffs, so there was an improvement. In the next step, we fitted the 5 snow parameters, and here we noticed that also things improved a little bit more, but still we have some negative nice subcliff outlet. So overall, our initial simulation had an overall objective function of 0.3 minus 0.3. After fitting lapses, P-labs and T-labs, we had a nice subcliff of 0.16, and after fitting the snow parameters, we had a nice subcliff of 0.2. So the improvement was small by fitting the lapse and the snow parameters. But notice that although the nice subcliff values are small, but the P factor and R factor are quite significant. As we fitted the snow parameters, we are accounting for more than 60% of our data, and P factor is quite meaningful. And R factor here, after fitting the snow parameter, is a bit large. Of course, we chose a very large band for snow parameter. Now, as you remember, the reason the improvement is small is because, as we discussed in the previous video, is that we had a lot of stations in the mountain. So when you are covering the temperature and the rainfall, the climate in the mountain, then elevation band and the parameters associated with elevation band are not going to make a significant improvement to the model. If we had no stations on the mountains, on the snowy mountains, the story would be completely different, of course. Now, with that, let's go to SWATCUP and continue with our calibration. And the next step we want to do is to parameterize each outlet. So, okay, we fitted our snow parameters and I fixed the values. And now, in order to see what we have, I'm just going to do the one run that I always do with the parameters sort of a generic parameter, and save everything. And then I make a one run at this is the end result of our T-laps and P-laps, and also snow parameter fitting, and we fix them, and now here is what we have. So let me just take a look. So based on this, we can parameterize our parameters. So for outlet number 6, I'm slightly overestimating in some places. Now in situations like this, where you underestimate some places, overestimate in some places, and so on, there is not a clear thing that you can do. Here, some places I'm shifting to the right, and some places shifting to the left, and so on. So here, the overall simulation, as you can see, is good. But the individual peaks and bases and shifts and so on, there are small discrepancies. And that's because there is a lot of things happening in the watershed. So we should not expect to match everything perfectly, right? I mean, because we're not accounting for all the processes that are happening in the watershed. This is a very dynamic area, and a lot of things are happening. But we can do some general improvements, such as decreasing the peaks here, and for the other outlet. So the base here seems to be a problem, so I could be increasing the base and maybe decreasing the peak again in some places. And for the next outlet, it's sort of the same story. Every outlet is quite okay in terms of dynamics, but there are a little bit of discrepancies. And for a busy watershed such as Danube that we are doing, this is of course expected. But we are going to do the best that we can right now. So I will try to decrease the peaks for outlet number 6, but now I need to parameterize it. Now, if you remember from before, so here is my outlet number 6 is here, and number 8 is here. So these are all the upstream subbasins for outlet number 8. And then for outlet number 6, I have all of these, plus these subbasins, 1, 2, 3, 4, 5, which all come here. So everything from here and everything from here comes into subbasin number 6. But for subbasin number 8, I have only to parameterize these subbasins, right? Because the rest of the watershed has no impact on what happens here. So for 8, I only need to calibrate the parameters upstream of number 8. And for number 6, I have to do these as well as the other ones that join number 6 at this point. So in order to determine the upstream, all the upstream subbasins in the utility program, we have upstream subbasin. So here, if you import files and you browse, what you get is a folder that tells you how to identify or how to determine all the upstream subbasins of an outlet. There is a README file that explains step by step what you have to do. It's very simple. So it says in the upstream definition file, enter number of subbasins, number of outlets, and outlet numbers. So what I have to do in the upstream definition, I have to just fill this information, and I have 54 subbasins, and I want 11 subbasins to know what the values are. And to get these numbers, I mean, you can go in one of your input files. For example, you can go to extraction, and in the extraction definition, you have all these 11 numbers. So I just copy this here, and I can paste it in here, right? It doesn't have to be vertical, it can be horizontal. So these are my 11 subbasins for which I want to to know the upstream sub-basins to these outlets. Save this. And then the next thing it wants me to do, if I go back to my file, it says open project, your ArcSWAT project, MDB file, and go to reach table and copy the column from to into this text file. So I have to go to my project, and my project is just right here. Project, and go to my MDB file and get the reach table here, and from node to node. So all I have to do is copy these two columns into my from upstream from to text. So I copied those, just paste it here, right? Save. And then the next thing I have to do is just to run the program. And when I run the program, I get upstream out. Now in this file, for every outlet, say number 6, there are 20 subbasins above number 6. This is outlet number 8. There are 14 subbasins number 8, and so on. So for every outlet, I get all the upstream subbasins. And as you can see, some of them are nested, say number 6 and number 8 are nested subbasins. So what I can just copy this conveniently, copy here, and bring it into my parim file, so I just have it here, and I can use it from here. Alright. So for number 6, we said I want to decrease the peaks. In order to decrease the peaks, which parameters do I have to choose? Usually, to get these parameters, I go to K School Google Scholar, and I go to Google Scholar. Here you can have access to all of our papers, and this is a little bit of self-advertising, but it's quite practical. Here is the European paper, and they are all free, so you can access them quite easily. And then in this file, if you can open, for example, the PDF file, let me not download it, I can just look at it here. I have a table in here where it gives you a list of parameters that you can use for different occasions. So in this table, if I can find it right here. So in this table, I have, for example, if base flow is too low and evapotranspiration too high, then you need to check these parameters. You need to decrease groundwater minimum threshold and decrease groundwater revap and increase revap minimum and so on. So if your base flow is too high, then you have to do the opposite of what it says here. So in my case, the peak flow is too low. If peak flow is too low, then I have to do this. In our case, peak flow is too high, then I have to do the opposite of what it says here. So I can just copy from here, and in my parinf, I can just paste this. All right. So for CN2, I would make let me make this a bit larger. So in CN2, we always want to make a relative change to CN2, right? And then I need to, in water storage capacity, we also make a relative change to all the soil parameters always. Now, ESCO usually SWAT uses the same everywhere, so you can make a relative or a value change. For ESCO, values less than, let's say, 0.6, the range is 0 to 1. Less than 0.6 is usually for desert areas, so you want to be bigger than between 0.7 to 1 always for a normal, average watershed. So what I had to do is to, here it says to increase, so I need to decrease it. So to decrease it, I go from minus 0.3, let's say, to 0. Now I cannot change the 0.3 is also a bit too much, maybe. You should go to SWAT input-output manual, and there you can see that CN2 depends on your land use and also the soil and so on. So it's a parameter that you cannot change too much because you already have your soil map and your land use map. Maybe there is a slight differences in each sub-basin, but you cannot change it from 20 to 90, for example. You cannot have a very large change in CN2. Now, what I can do here is, what I should do is that always I should look at the values that I already have in place to make sure that the changes that I'm making are not too drastic or meaningless. So for CN2, for let's say number 1, if I go to number 1, management, so CN2 has a value of 66, right? And I want to decrease that a little bit. So it's already sort of average. CN2, as you know, can range from 20 to 90. So I can decrease it a little bit. So I want to go from 0 to minus 0.3. And the water storage capacity, I need to increase water storage capacity. So water storage capacity is, so if I open a soil for sub-basin number 1, and you can see here water storage capacity is between 0.1 for the first layer and 0.01, so I can increase it a little bit, 0 to 0.5, right? And then you should see what it means when you go to 0.5. So when the value is, for example, 0.1, a relative change would be 0.1 times 1 plus, let's say the maximum value here would be some number in between here. And the maximum would be 0.5. So 1.5 times 0.1 times 1 plus 0.5, so that would be 0.15. So it is not an unrealistic change to this. And for ESCO and in HRU, what is my value already? My value already is ESCO is already 0.95, and I need to increase that. So there isn't much room to increase this. So perhaps I don't need to touch this parameter. So I don't probably need to do anything here because it's already sort of at its maximum. And you also know that the absolute value gives you a range of the parameters that you can have. I mean, SWAT edit does not put anything beyond this range into the SWAT files. So here you need to check this, and CN2 ranges from 35 to 98. Sometimes this goes from 20 to 90. I mean, depending on your situation, you can edit this file, but once you edit it, then nothing beyond these values can go into the SWAT input files. So this now I want for number 6, right? So for number 6, these are the upstream sub basins. So I can copy this here, and 1, 2, 3, 4. That's where the sub basin numbers go. I can simply put these values here, and for the soil also 1, 2, 3, 4. Control V, and this is the for sub basin number 6. Now for sub basin number 8. As you recall, I wanted to increase the base and decrease the peak. So if I go to my file here, so increase the base and decrease the peak. So this is for shift. Here it says if base flow is too high and peaks too low. Actually, I have the opposite of this situation. So I want to know the opposite of what it says here, right? So I want to know the opposite of what it says here. Again, I can copy this and paste it in my file here. So it says increase CN2, but I want to decrease CN2. So let me give the ranges. I want to decrease, so it's similar to the one above. So minus 0.3 to 0. Decrease CN2. It says decrease soil water storage capacity. I want to increase it, so a similar situation. So I can go to 0 to 0.5. Increase it. It says decrease SO. I need to increase it. We talked before that this is already at its sort of maximum, so we forget about this one. And then groundwater QMN, it says to increase, which I want to decrease. So let me see what its value already is. Groundwater QMN, and I want this for number 8. So let me look at number 8. Subbasin, number 8 subbasin, groundwater. So number 8 subbasin, and the groundwater would be here. And what I would like to do is to decrease groundwater QM. Groundwater QMM is 1,000, and my initial depth is also 1,000. So I need to decrease this. So maybe I can go from 0 to 500 because it's already 1,000, and I need to decrease it. And then I need to decrease groundwater revap. Groundwater revap is 0.02. So the minimum value of this groundwater revap is already 0.02. So there isn't much that I can do here. So I can eliminate this from here. And then I need to increase revap, revap PMN, that's here. I need to increase that. So this is 750. Initial is 1,000. So I can maybe go here from 1,000 to 2,000. Increase that, right? Groundwater parameters are something we really don't know anything about. So it's just, we just have to fit them. So that is that. That's how I parameterize number 8. So let me get rid of these signs. And then number 8, these are the upstream subbasins. So again, I can copy these, and 1, 2, 3, 4, Control V. And the same thing, I can maybe just copy this here and paste it here, and paste it here, and paste it here. And then CN2, of course, is a relative change. Soil water is a relative change. And groundwater QMN, we decided that it would be a value change, and this also a value change. Now, notice that these are nested outlets. So I have 1, 2, 3, 4, 5, 6 for number 6, and then 7, 8, 9, 10, all the way to 50 is this one, number 8. So what I have to do is just get rid of this, because I'll be calibrating those for number 8 subbasin. So I can just get rid of everything here, right? So I will, what I'm doing is I just, I calibrate for number 8, I have to calibrate this upstream of 8. When it comes to 6, I already did this for 8. This comes into 6, and then 6 has these extra subbasins here that I need to calibrate those. So that, right, makes a lot of sense. Now, if the number of subbasins is small and the whole watershed is small, this is easy to do. You can just visualize it. But if it is a large watershed, this is not easy to do. So if you go back into this upstream folder in the utility, and you know where this is now, right? This is in your project, in your SWATCUP project. Before we had an ArcSWAT that had your map in there, and now we have a utility program which has your this subbasin upstream here. Now there is another program, it's called Subtract Subbasin, and for Subtract Subbasin, if you have two nested subbasins and you just want to eliminate all the common ones, all you have to do is from here, now we are interested in number 6 and 8, so I can just copy these 6 and 8 and paste it into here, into this subtract, and then all I have to do is to just run the subtract program, and what I get is those subbasins which they don't have in common. That has to be fitted for the other outlet, right? So this is very conveniently done for you, so you don't have to do manually and spend a lot of time here. So these programs are to help you not to spend too much time on extra issues that take a lot of time actually to do. And so you have more time to spend on your analysis instead of doing preparation of databases and doing all these other extra that take a lot of time and are just chores that you have to do in order to get to the main thing. I also see some people are trying to replicate SWATCUP and write it in R script or something, which I think is a complete waste of time. I mean, why do you want to do something which is already done? You should use this and address other important scientific issues. I mean, if you're a master's student or you are a PhD student, then you should spend most of your time on scientific analysis rather than on programming and so on, especially programming things which is already done. Anyhow, so all of these tools, utility tools which we have here, and I will address them. I've already addressed the make observation file, and I have addressed make elevation band. There is best management practice and the hourly, which we will address later. So now I have then parameterized this for the things that I visually can see, right? I mean, I can see that I need to increase the base, decrease the peak here, and I can see that I need to decrease the peak here. So for that we have specific parameters, but there are a lot of other things for which I really don't know. There is no real parameter here. In a minute I will tell you more about the base flow. Base flow is quite tricky and important, and in some of these outlets, you see we have a base flow problem. See here also we have a base flow problem. So we will have a little discussion about base flow. But now that I have done the obvious parameters, usually I take a number of other parameters so that I can explain perhaps some of the discrepancies here and there, the small changes and discrepancies that you see. So for this, I have prepared like a list of these parameters down here that I can just take and some ranges. I can just take these, copy and paste here for this. And also for here, for the two outlets, just add here and just add the subbasin numbers to them. So once I have done this, so you see the number of parameters can increase rapidly if you have more and more observed outlets. But now what you have to do is to check the ranges. I mean, these ranges I have sort of based on my experience. What you need to do to set the ranges is, first you have to consult what ranges there are already. So you have to go, for example, to groundwater and see what value the parameter already has. Then you need to check the value of that parameter, the absolute value in this absolute SWAT value file. And then you have to see if you want to increase it or decrease it, or what the difference is, how much you want to increase it. And based on that, you have to come up with the ranges. There is no hard rule for this. So you just have to get a feel for it, for your project, and see what works for you and what doesn't. So having this, now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters here, and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 parameters here. So I have 22 parameters here. And these extra parameters that I chose, as you can see, there are some of them have to do with soil hydraulic conductivity and bulk density. So there are soil parameters. There are a few parameters here that shift the simulation a little bit to the right or to the left. And there are a number of groundwater parameters that can adjust probably some of the recession curves and so on and so forth. So these are some of the parameters that you can fit at the same time together. So for 22 parameter, I would probably make one large number of simulation. So I have about 8 CPUs, and if I run 100 simulation on each, I would have 800 simulations for this iteration. But this is something that you don't have to do 10 times. I see some people just keep doing this over and over and over and make 20 iterations. You only need 3 or 4 iterations, that's it. And if you cannot get to a reasonable result in 3 or 4 iterations, then I think you need to go back to your model and check your data and the processes that you have included in the model. So let's just go here, save everything, close everything, and do a run, and we'll see what we get at the end. All right, my simulation is finished of the 800 simulations. Now I can see the result by going to single objective post-processing. Let's see what we have. This takes a bit longer because of too many simulations and parameters. All right, so I can run 95 PPU plot, and that's what I have, right? For outflow number 6 and outflow number 8, and the rest of the outlets, which I didn't parameterize, so we should only look at those first 2. And these ones, they are not on the same river network, so the changes we made upstream do not affect these, so you get no uncertainty band here. Let's look at the summary stat. The summary stat, I got the overall NISOT cliff of 0.33 almost, which is a good improvement from 0.2, what we had before. And also now you see that all NISOT cliffs for all the outlets are positive, but we are really should be looking at the first 2. And the first 2, the NISOT cliff of 0.19 and 0.22 we have now. But the important thing we should look at here is the P factor and the R factor. NISOT cliff is just the simulation. It's just the comparison of 2 signals, the best simulation and the observation. But given the uncertainties that we have, we should be looking at P factor and R factor. So P factor here for number 6 is 0.55. That means 55% of my observation falls within my simulation. And for 8 is 0.71. That's 71% of my observation falls into the simulation. And the R factors are around 1, so they are quite reasonable. The uncertainty is quite low. for this run. So remember in the past videos, usually we would like to have a P factor of larger than 0.7 and an R factor of around 1. So we almost satisfy that criteria. So if you look at the graphs again, here you could really ignore the red line, which is the best simulation. I have this here for historic reason, but we shouldn't really be looking at the red line. What you should be looking is the green band. That is your simulation. And then the observation is in blue, so you can see what percentage of the observation falls within your simulation, which is represented by the green band. So try to mentally ignore the red line. And for number 8, similarly, you have to see how much of the blue falls into the green band. So there is room for improvement, of course. So we have to look at the statistics, which we have. We can improve these two numbers probably a little bit more. Now, here, to go forward, we can follow a number of strategies that I have to show you one by one, and things make it a bit complicated here. But you have to know the situation. Number 8 is upstream. Number 6 is also upstream of all the other outlets. So 8 feeds number 6, and then plus these. So what I can do here is to just first calibrate for subbasins that feed outlet number 8, right? And then keep the ranges of parameters which I have calibrated, add then number 6 parameters to it. So then I have the best thing for number 8, and then by calibrating the rest of the subbasins, I will have the best simulation for number 6, and then I can go forward in the same manner. Because here we have quite a bit of nested outlets. So to show you these one by one, I'm going to refer it to the next video, because this video is getting too long. So let me just show you again that where we are. And so we have done the first iteration, and we are now looking at number 6 and number 8 outlets, and we are trying to design strategies to go forward. So see you in the next video. Thank you for watching.